Okay, in this video we're going to look at three different theorems, and the first theorem we're going to look at is a review. We already looked at the intermediate value theorem. Okay, the second is going to be Rolle's theorem, and then we're going to spend a majority of our time in this section in future videos looking at the mean value theorem. Okay, so the reason why intermediate value theorem is a review is that this was the major theorem, major continuity theorem. So in our continuity chapter, we looked at this topic, okay? And we're going to look at Rolle's theorem. Now, Rolle's theorem and the mean value theorem are going to be special in that they both connect, and they make a connection between the average rate of change, so average rate of change, and instantaneous rate of change. So they draw conclusions about how these are related, and this is a very important connection. So instantaneous rate of change. Okay. So let's dive right into these theorems right here and look at examples of each. Okay. So to review, the intermediate value theorem, please feel free to stop and pause this video if you want to write down this definition. You do have the definition from chapter 2. So basically, when we're looking at the intermediate value theorem, we're taking, let's just highlight some important information here. So the function is continuous, okay? So whatever our definition of continuous is for a continuous function, this function is continuous on the interval from a to b, and there is some number n, okay? And we're going to call this number n over here. Between f at a and f at b, okay? So it's sandwiched in between f at a and f at b, where and we have to make sure, this is just kind of an important piece of information. We know that f at a and f can't equal f at b. Then there is some number c, okay? There is a value c such that in the interval between a and b, such that if you evaluate the function at c, it's going to give you a value n, okay? So if we want to go back to the practical example to this, the practical example was the FAT project. If you remember the video about the FAT project, that someone was going to try to gain as much weight as they possibly could over a period of time. Okay, and if they wanted to, say they wanted to gain 30 pounds over 30 days. So this would be a chart of their data. So this is the days, and then this would be their weight gain. And let's say the data went something like this, and then it increased. Okay, so they gained over time. So let's just say that the woman who was trying to gain weight, we know that she was somewhere between 6 and 22. Okay, so that's our F of A, and F of B. Okay, so that means that if I take, so let's say on day 2, she had gained 6 pounds, and on day 28, she had gained 22 pounds, okay? So on day 28, she had gained 22 pounds, and then on day 2, she had gained 6 pounds. That's just saying if I pick some value in between here and here, let's say I happen to pick, let's say I pick 14, okay? It's not necessarily drawn to scale here. Then 14, if I take that value across here, all this theorem says is that 14 will fall somewhere between the 2 and the 28. That there will be some value. That she gained 14 pounds somewhere between 2 and 28. Okay, so that's just a physical interpretation of this. So this is not new. The next two theorems will be new. Okay, so the next two theorems that we're going to look at are called Rolle's theorem and the mean value theorem. Now what's different about the Rolle's theorem, and they're very much connected, but basically, I'll draw you a picture in a second. The mean value theorem is a slanted version. It's a slanted version of Rolle's theorem. Okay, so I'll explain Rolle's theorem, and then we're simply going to add a slant to the problem, and the same thing for Rolle's theorem will apply for the mean value theorem. Okay, so we went through the intermediate value theorem. Now let's look at Rolle's theorem. Okay, so in order to look at Rolle's theorem, we're going to take this definition right here and draw a picture of it. So let's analyze this. So first, we know the function is continuous on an interval from a to b. So let's draw an example of a function that is continuous from a to b. Okay, I'm going to be a little bit careful here because I need to read further along to know how to draw this. Now, it says specifically here that f at a is equal to f at b. Okay, that was not the example back here. Okay, f at a and f at b were not equal. Now, f at a and f at b are going to be equal in this case. So let's pick this value right here. So let's say here's a and here's b. So we know that the height of a and b has to be the same. Okay, f at a has to equal f at b. So now I'm going to draw myself a continuous function. You can draw all sorts of functions, but I'm going to have it just go up. It's going to come up like this, and then it's going to come back down here. And we know f at a and f at b are equal to each other. Okay, so what this theorem says is that suppose f is continuous and differentiable on the interval. So this is differentiable, and I can draw slopes of tangent lines. Then if f at a equals b, then there has to be a point where the derivative is equal to 0. Okay, and this is very reasonable because right here, doesn't that make sense? That this derivative is going to be 0 right here. This derivative, the slope of the tangent line here, is 0. And it has to be a value c. So it's saying, Rolle's theorem is saying, if you take a graph and the f of a is equal to f of b, then there is going to be at some point between a and b, a point, and we're going to call that point c, where the first derivative is equal to 0. Okay, so that's Rolle's theorem. Now, I'm simply going to take Rolle's theorem and we're going to slant it. So this is what I mean by slant. I'm going to take this graph, and instead of it just being over a to b and coming back, in this case, f at a is not going to equal f at b. Okay, so over here, if I were to graph this, this is going to be f at a here. Okay, and this is going to be f at b right here. Okay, so let's get into what the mean value theorem says. And this is the theorem that we're going to spend most of our time on. The mean value theorem says it's continuous at every point over the interval from a to b and differentiable. Then there is at least one number c. Okay, same type of scenario. There's a number c between a and b. Okay, such that now here is the slope of the secant line. We know that we find the slope of this line right here by simply subtracting your y values, okay, over your x values. So f of b minus f of a is my slope over b minus a, okay? And then that is going to be equal to this line right here, which is the tangent, okay? So what we've just made is this big connection idea. This right here is average rate of change. That was the way we find average rate of change, slope of a line, okay? Now, this is slope at an instant, okay? This is instantaneous rate of change. Instantaneous rate of change. Okay, so basically, this is saying that there is some number. It doesn't tell you how to find that number, okay, but there is some number between A and B such that the slope of this line right here is going to be parallel or equal to this line right here, okay? That is the big concept, okay? Now let's apply this to an example. Let's show that the graph of x squared satisfies the mean value theorem on the interval from 0 to 2. Okay, so in order to do this example, we're going to get a graph. Let's get a graph going here first. And if we graph the function, it's only from 0 to 2, so I only need the right quadrant. So I'm going to go from 0 to 2. I know if I go up 0, 0, I'm going to go up 1 and up 4. Okay, so my graph is going to go something like this. Okay, so we're going to try to show that from 0 to 2 that this function satisfies the mean value theorem. So let's find the average rate of change first from 0 to 2, okay, which would be this graph right here, okay? So I'm going to find the average rate of change. So the average rate of change is going to be equal to, so this coordinate's 2, this is 1, 0. I'm going to take f at 2 minus f at 0 over 2 minus 0, okay? So I've got 4, 3, 2, 1 there. All right, so f at 2 we know is 4. F at 0, we can plug it in here. We can look at it graphically, is 0. And then I have 2, okay? So I know that the slope of this line right here is 2. So the slope of this secant line is 2. Now what the mean value theorem says that at some point on this graph, okay, we don't know exactly where right now, but some point on this graph, the function has a tangent line that is going to have equal to a slope of 2. Okay, so let's think about that. I need to find out what the slope of this line is, but I know that this slope needs to be 2. But I need to know, well, what value is it for C? That's what I'm trying to find. Okay, the mean value theorem doesn't tell you how to find it, so we have to use calculus to find it. But we know that it should be equal to 2. So if I'm going to take a function of x, okay, f of x is x squared, then I know my derivative is going to be 2x. Now, I want my derivative to equal 2. So 2x is going to be 2. That means at x equals 1, at 1, it takes on a slope of 2. Okay? So that's the big concept. The mean value theorem basically here is saying when does the derivative at C equal the same value as f of b minus f at a all over b minus a, okay? That's the mean value theorem here. We just showed that it does take on this value here and here. So if you just wanted to clarify, okay, it happens at 1. So for this graph, it occurs at x equals 1. And the equation of the line parallel to the secant line, the equation line parallel to the secant, okay, we could calculate what's parallel to the secant line, so let's do that. So if I want to be parallel, I know I'm going to have a slope of 2. I know I have a slope of 2, and I also know that it goes through the point x is 1. So when x is 1, it's going to be the coordinates 1, 1, 1, comma 1. So then I'm going to say y equals 2x plus b. I'm going to plug 1 in, equals b. So that gives me an equation of b equals -1. So the equation of that green line, let's put it in green here. The equation of the green line is y equals 2x minus 1. Okay, and so that's the basic gist of the mean value theorem. Okay, I just want to talk about one more example with a mean value theorem that will give you kind of a physical application to the mean